Okay, so there's a couple different ways to make the final proof that you need to in this adventure, but the one that we're going to work on right now is going to introduce us to the concept of a reflection. And a reflection is a transformation, and we're going to learn about it a little bit more here. So what I have created for us is an angle. This is angle BAC, or it could be called angle CAB. Since it's the only angle really we're looking at, somebody could call it potentially angle A. Okay, I'm going to move A around to this side on the outside there. Okay, so the next thing I'm going to do is I'm going to bisect the angle. So what does it mean to bisect the angle? Well, it means to cut the angle in half, really. And this is a line that bisects the angle. There could be a ray that bisects the angle, but this is a line that bisects the angle. So how do I know that it's cut in half? Well, I can place a point there, and I can measure both of the angles, okay? And you could see that, as we move this angle around, that the bisector moves too, to make sure that in all cases the two parts that the bisector creates are equal to each other. So this is an angle bisector. So now what's the usefulness of this? Well, it turns out what's going to be useful is that if I place a point over here, let's say on this side of our angle BAC, and I did something called a reflection, right? A reflection then is we're going to reflect it about a line. What that means is across. Another way to say it might be to say across the line. We're going to reflect this point across the line. I'm going to just make sure that we have that ready. So here's the reflection tool, right? We're going to reflect here. I'm going to select the object. We're going to reflect. That's point E. And I'm going to reflect it across the bisector. Now, where do you think it's going to land? So this is kind of interesting. That you can see here that it is called E prime. That little apostrophe mark that comes after it tells us that it is the image of E after the reflection. So we call E the pre-image and E prime the image. And that E with the apostrophe is what we call prime. If we reflected it again or did another transformation to it, we would call E double prime. But you notice it has the same name, the point, okay, and that it is E double prime. So now, what do we have going on here? Well, let's talk about that. Let's actually make a segment connecting the reflected parts, okay? And you know what? Let's find the point where that segment intersects this reflected line, okay? And you know what? Let's make segments between, for each of those points. So we're connecting E to this point, what is it? Intersection point F, okay? And then F to E prime over here. So now, what I want to do is, I think we're going to measure the length of EF and measure the length of FE prime. And let's take a look. We're going to use this distance or length tool, and we're going to measure. I just want to measure. Let me try hitting tab, see if I can. Now, let's see if I can measure that length. I don't know if that's the length of the whole thing. Well, we're going to try measuring this one here. Oh boy, here we go. I better undo that again. Alright, hold on. I've got to be able to view the algebra here. And then what I'll do is I will take that first segment. There it is. I'll take that off so we don't even have it. Okay? And I'm going to take this text thing and get rid of it. I don't want that. Oops. That's not what I wanted to get rid of. Yikes. Alright, so let's delete that text. Alright, so here we go again. From F to E. What I like is, with the algebra showing here, it shows me the actual length of E to F, right? And E prime to F. And you can see, let's try this again now. We're going to do the distance of just that segment. It's 2.58. And do the distance of just this segment. It's also 2.58. So now, what happens if I change all of this? You notice that as I change where E is, and the measure of those angles are changing, but what happens is they remain equidistant from this point here. So there is an equal distance from E to this intersection point and E prime to this intersection point. And what is this intersection point? Well, one other thing I think I'll show you is we'll measure this angle here. I wonder what that angle measures from DFE. Well, you can see that symbol comes up and tells you that that is a 90-degree angle. And of course, that means this one here, which is a linear pair to it, is going to also be 90. But we will just measure that to be sure and see it. And you can see they're both 90-degree angles, right? So we can kind of get that out of the way over there. Okay, so now notice that the reflection then is going to take the object, move it along the perpendicular line to the line of reflection, and land it equidistant on the other side, still on that perpendicular. This is a perpendicular line. EE prime is perpendicular to AD, to the line of reflection. We're seeing that because of these 90-degree angles, right? So, and then what we're just doing is we're just making sure that it's always equidistant, right? So this is a rule about reflections. Okay, it's part of the definition of a reflection. So the definition of a reflection, in part, says that it takes the object across a line of reflection and along the perpendicular to the line of reflection, places the object equidistant on the opposite side of the line of reflection, still on that perpendicular. So that's the concept there, okay? So now let's take a look here. So if I were to, this is what our task said we had to prove. So I'm just going to take a segment here, right? Now, if I were to take the perpendicular bisector to it, so let's take the perpendicular bisector to this. So what that does, by definition, the perpendicular bisector bisects this segment, it cuts it in half. So our question is, why, if this is cut in half here by point I, and this line here is going to be perpendicular, how can we prove that if we place a point here, J, on that perpendicular bisector, that the distance between G and J will always be the same as the distance as H and J? Well, let's just see. First, I'm going to just let us see if that is true. So we connect it here. We see that's true. And we connect it here. And we see that's true. Well, we see those are there. But let's measure them, okay? Let us measure the length of these two segments. And we can see, yes, they are equidistant. Now, what happens if I change J? Doesn't matter. They stay equidistant, right? What happens if I change the length of the original segment? Won't matter, okay? As long as J remains a point that is on the perpendicular bisector to the segment, it will always be equidistant to the endpoints. This is really, really important to know. Now, our question is, why? Can we prove it? And how would we prove that? Okay, let's start talking about that here. So the first thing we're going to put in here is we're going to say that we know that, I better use the right terms here. We're going to say GI is equal to HI. And how do we know that the distance from G to I is equal to the distance from H to I? Well, that is the definition of a perpendicular bisector. Really, if that is where the perpendicular bisector crosses the segment, then we know it divides GI and HI into equal parts, okay? So we know that GI is equal to HI. Well, also, we know that the measure, so we can go, the measure of angle GIJ is equal to the measure of angle HIJ. So we're talking about GIJ is equal to, oh boy, didn't mean to do that. GIJ is equal to HIJ. How do I know that? Well, again, by the definition of a perpendicular bisector. Okay? And that means this has to be perpendicular, so they both have to be 90-degree angles. So therefore, what can we conclude? Well, we have a point that is on the perpendicular to a line that is equidistant from another point that's on the perpendicular to the line. So we can conclude that G, let's see, H, we'll say, is a reflection of G. Okay? And that is by the definition of reflection, right? It is the result, I better say this, is the result of a reflection. Okay? So we would know that. Let's think about this now. What about J? Point J. What do we know about J? Well, J is also, if you were to reflect it across the line, where would it land? Well, perpendicular to it, it would have to be there, and its distance from the line would have to be 0, because its distance from the line now is 0. So if we reflected it across the same line, J would also be, and so J is the result of a reflection of J across the same line, and that's by the definition of reflection as well. Let's say okay there, and let's see. So we kind of got some logic here we're building. G is a result of the reflection here, so J is also a result of the reflection there. So if I drew a line, guess what that would mean? All of the points on the line, right, would also be reflections across the same line of reflection. In other words, we've taken the two endpoints of a segment and we've reflected those two endpoints. So therefore, we would conclude, what could we conclude here? Well, what I'd say is that, let me put it in here. So segment GJ, and this is not proper notation, but I'm just writing it out. Segment GJ is I'll say segment HJ is a reflection of segment GJ, by the definition of a reflection, right? So if it's a reflection, now we have the concluding piece here, right? Reflections, by definition, preserve congruency. Preserve congruency. And they are, I'll put this in here, reflections are a rigid transformation. So what does that mean? So what that means, and when we say preserve congruency, we mean it preserves measures, right? I put that in here. Preserves measures. And if we say that they are a rigid transformation, that means that the measures are not modified in any way before, pre, or post reflection. Okay? So they're always going to be the same. Okay? So now here we have basically our proof that says segments or points that are on this line are always going to be equidistant. How do we know that? Because they are part of a segment where the endpoints are a reflection on each side. This segment here, J, which has endpoints G and J, is a reflection, can be reflected over and would become K. So that's a rigid transformation, so it preserves congruency. So I know that's kind of a lot to think about, but it's one way, and it helps us understand the concept of reflection, and it's the way that we're going to try right now, just to prove that any point, okay, on the perpendicular bisector is always going to be equidistant from the endpoints using that proof.